All right, hello Algebra 2. This is a practice quiz. We're going to have our actual quiz on Friday, so I'm going to walk it through with you. Feel free to pause, skip, kind of jump around to whichever questions you feel you need help on. So looking at number 1, it says y equals 3 to the x plus 1. If I think about what's the basic or the parent graph of this function, that would be y equals just 3 to the x. And remember, this is an exponential equation. It comes in the form a times b to the x. And so that's looking at it as like 1 times 3 to the x. So our y-intercept would be 0, 1. And then exponential growth, this one is going to model. So I know it's going to increase. And then for all basic parent graphs of exponential functions, they have an asymptote at y equals 0. And now if I'm looking at how does this graph change, this one would move left 1. So I'm going to take that point 1, 0, move it to the left 1, move all the other points to the left 1, and the asymptote would still be at y equals 0. Okay, number 2. Number 2 still has the same parent graph over here. So we're going to have 0, 1. It's going to increase exponentially. And then if I'm looking at what does the negative do, well, that's going to flip it over the x-axis. So I'll flip it over the x, and it'll go down like so. And I notice that the asymptote is still at y equals 0. So y equals 0. And if we look at number 3, if I'm asking what is the basic or the parent function, and just so you guys know before Friday's quiz, it's really good to have these memorized. Basically the basic parent function of an exponential and a logarithm. So this would be y equals 2 to the x. I know that this models growth. My y-intercept is going to be 0, 1. And my asymptote is going to be at y equals 0. And so I plot that, but now I need to see how the function's been transformed. The negative will reflect this over the y-axis since it's with the exponent, and the plus 2 means it's going to move it up 2. So the y-axis is going to be this one, so all these points are going to get reflected in this manner, and then we need to go up 2, 1, 2. So now all of these points are approaching y equals 2. So you can erase kind of your preliminary work and make sure you have your final graph graphed. And then I can see that that asymptote, it's horizontal, which is true of all exponential equations, and that's y equals 2. All right, looking at number 4. Number 4, this is the parent graph, and this differs from the other ones because if I look at y equals a times b to the x, remember the y-intercept is 0, a, so in this case it's 0, 2. It still models growth, and for all parent functions, the asymptote is y equals 0. So I'm going to go to 0, 2. And it's growing. Actually, I can just go ahead and bold this in because this has not been moved left, right, up, or down in any way. And the only difference here really is that I have a y-intercept of 0, 2 instead of 0, 1 like the other ones. And this asymptote would be at y equals 0. All right, moving to the next one. So looking at the next one, this one's different in the way that it models decay. This one models decay. I know that because the b value is less than 1, if you're thinking about this again as y equals a times b to the x. My y-intercept is still 0, 1, and my asymptote is still at y equals 0, but the only difference here is now it's going to decrease as you move from left to right. Come on, there we go. And my asymptote is at y equals 0. All right, number 6. Number 6, sorry, these parentheses, I'll fix this in the actual document, but they should be raised to the x plus 2 here. So my parent function is y equals 3 to the x, meaning my y-intercept is 0, 1, my asymptote is at y equals 0, and I know that this is going to model growth. So I have 0, 1, da, 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 da. Notice I'm doing this in dash because I've got to actually transform it. So this plus 2 with the exponent is going to move it left 2 units. This minus 1 is going to move it down 1 unit. So we're going to go left 2, down 1, which means all these other points are going left 2, down 1. And now instead of approaching 0, they're approaching negative 1. So there's my asymptote. It's going to be at y equals negative 1. All right, number 7. Number 7, this is a log graph. It's the inverse of an exponential. And we need to remember that for any basic log graph, this is a parent function. When nothing's been added or subtracted, the x-intercept is 1, 0, and the asymptote is always x equals whatever's been added or subtracted from the x. Really, it's whatever's been subtracted from the x variable. So in this case, it would be 0. So I have to graph the logarithmic, which is 1, 0, and then it's the inverse, so it's reflected over the line y equals x, or you just always have to remember this shape. And then there's that asymptote, which is at x equals 0. Okay, number 8. Number 8, I can use that parent graph, or let me just go ahead and list it. The basic graph is y is equal to log base 2 of x, which has a point at 1, 0 and a vertical asymptote at x equals 0. But now this plus 1 with the x is going to move the graph left 1 unit, meaning this point, the 1, 0, gets moved to 0, 0. All these points get moved left 1 unit, and now it looks like this. And if I'm asking what is my vertical asymptote, remember it's what's been subtracted from x. So in this case, I can see it's going to be x equals negative 1. Remember, a minus and negative creates that positive. Okay, number 9. My basic shape is going to be y equals log base 6 of x. Again, with a point at 1, 0, looking like this. And then the minus 2 is going to move the graph right 2. And that minus 1 is going to move the graph down 1. So I take that point and I go right 2, down 1. All these other points are going to go right 2, down 1. So now they're approaching, so they're looking like this. And they're approaching the vertical asymptote. Again, think what's been subtracted from x? 2. So they're approaching the vertical asymptote, x equals 2. Okay, moving on to number 10. Number 10, my basic graph that I want to start with and then move it is log base 5 of x. Again, we start with the point 1, 0. This is my basic graph. And if I look at this negative, that's going to reflect it over the x-axis, upside down. So I reflect it over the x, meaning all these points here get moved up here, and all those points get moved down here. And there is my logarithmic graph. Notice that my asymptote, there's been nothing subtracted from x, or you can think 0's been subtracted from x. So it's going to be x equals 0. Number 11, again, my basic graph is y equals log base 5 of x. So that's going to have a point at 1, 0 and go like this. The negative with the x is going to reflect it over the y-axis. So this point is going to get moved over the y-axis along with every other point. All these points. Oh, I should still do it in dash actually because I'm not done with my transformation. That. And then this one here is going to move the graph up 1. So I take this point and move it up 1 along with every other point, and now here is my actual shape. And let me erase that so I can get that actual shape. Notice that that vertical asymptote, what's been subtracted from x, 0, or you can even visually see it on your graph. It will be at x equals 0. All right, moving on to number 12. We learned this in section 8.1b. It says write an exponential function in the form y equals ab to the x that includes these points. Okay, first thing I notice is this is an xy point, and this is an xy. First thing I start with here is I have to plug in x, oops, it's supposed to be highlighted, plug in x and y in for x and y. So I have 75 is equal to a times b raised to the second power. And then we always solve for a. So a has been multiplied by b squared. To undo that, I'm going to divide by b squared. And that gives me a is equal to 75 over b squared. And I like to bubble this because I know I'm going to come back to it later. Second step, take your other point, also plug that in for x and y. So I have 15, we'll do that here. 15 is equal to a times b raised to the first power. And now I want to take this guy and plug it in for a. And so that'll really be 15 is equal to 75 over b squared times b to the first. Or you can think b to the first over 1. And then as I'm going to go ahead and simplify that. I notice a b to the first and a b squared. I can reduce that. So let's go ahead and do that. This will be just a b to the first. So I really have 15 is equal to 75 over b. And now I can go ahead and solve for b. You have two options here. You can go ahead and put this number over 1 and use the cross product property, or you can multiply b out and then divide by 15. Up to you. I know from geometry a lot of us like the cross product property, so I'll go ahead and do that here. So that'll become 15 times b is equal to 75. Divide by 15, and I can see that b is equal to 5. Now I like to box b because that's one of my major points. After you have b, you're going to plug it back in to solve for a. So we have 75 divided by b, which is 5, squared is equal to a. That's just 75 divided by 25, which is 3. And then your actual answer, because it says write an equation in that form, is y is equal to a, which is 3, times b, which is 5, raised to the x power. All right, moving on to section 8.3, change to exponential form. So one of the things you want to keep in mind is if you have b raised to the x power is equal to y, then you know that the logarithmic statement, that's also true. So this is equivalent to, I'm just going to do a double arrow. This is equivalent to log base b, remember the base is the guy holding up a value, of y equals x. The log always gets the exponent by itself on one side of the equation. Okay, keeping that rule in mind, let's go ahead and do this. So number 13, change this to exponential form. So my base is the little subscript. I have 3 raised to the y power is equal to x, and that's it. Number 14, x raised to the mth power is equal to 10. Now change to log form. So the base becomes the subscript of the log. So it'll be log base 10 of 1,000 gets the exponent by itself is equal to 3. Now, because the base is 10, you could have just written this as log of 1,000 equals 3, and that's good too, because when there's no base written with a log, it's understood to be a base 10. Number 16, this would be log base e of m is equal to x, and Log base e is actually equivalent to something else on your calculator. That's equivalent to an ln. So you actually could have had ln of m is equal to x. But I don't think we've learned that yet in Algebra 2, so I'd probably just be looking for this answer. Number 17, evaluate each of the following. So now when we're asked to evaluate, we have to determine what is the actual value. So in other words, I'm saying, hey, I don't know what this equals. Let's say it equals to x. And the easiest way to do this is to convert to exponential form. So again, my base is 3. I'm asking 3 raised to what power is equal to 27? Well, 27 is just 3 cubed. So 3 raised to what power would give me 3 cubed? That would have to be 3. So my answer, since there was no x there, I can just say it's equal to 3. Number 19, if I'm asking what does this equal? I'm asking 9 raised to what power is equal to 81? Well, 81 is just 9 squared. So that x value would have to equal 2. Number 19, I'm asking what does this equal? So I'm asking 2 raised to what power is equal to 8? Well, 8 is really just 2 cubed. And so my answer, again, we're looking at the exponents lined up. That answer is equal to 3. Number 20, I'm asking what does this equal? So I'm asking 7 raised to what power gives me 7? Well, 7 is just 7 to the first power, so in this case, x has got to equal 1. If I look at number 21, I'm asking what does this equal? So I'm asking 4 raised to what power is equal to 1/16. This one's a little bit tricky. You have to remember if we have 1 over a number, that means that we really have a base raised to a negative exponent. And so I have 4 to the x is equal to 16 to the negative first. And then I want to take and rewrite the number 16 as a base of 4. So if I have 4 to the x, 16 is really 4 squared. And now when you raise an exponent to an exponent, you multiply. So really what I'm going to have here, is 4 to the x is equal to 4 to the 2 times negative 1, which is negative 2. So this is actually negative 2. Number 22, if I'm asking what does this equal? I'm asking 3 raised to what power is equal to 1? And that would actually be 0. Through any number to the 0 power is equal to 1. So in this case, x is equal to 0. Keep on moving along here. Number 23. If I'm asking what does this equal, I'm asking 121 raised to what power equals 11? Well, 121 is really 11 squared. So if I rewrite this as 11 squared raised to what power is equal to 11 to the first? Remember, when you raise an exponent to an exponent, you multiply. So I'm asking 11 raised to 2 times what value will equal 11 to the first? Well, once I have this and this, I can just set up the equation. 2x is equal to 1, so x is equal to 1/2. And so that answer is 1/2. And then number 24, I'm asking 9 raised to what power is equal to 1/9? Again, 1/9 is the same as 9 to the negative first. So my answer would be negative 1. And then 25, I'm asking what does this equal? So I'm asking 64 raised to what power is equal to 4? Well, 64 is really 4 to the third power. When you raise an exponent to an exponent, you multiply them. And now I have my exponents equal, so I can set them equal to each other. 3x equals 1, x is equal to 1/3. So the answer of this log is 1/3. All right, one more page. Find the equation of the inverse of the given function. Remember your steps to finding an inverse. Step number 1 is to switch the x and y. So if I switch the x and switch the y, I would have x is equal to y squared plus 3. That is your step 1. Step 2 is to solve for y. Maybe I should be writing these down. Switch x and y, solve for y. So how do I solve for y? I need to subtract 3 from both sides, which gives me x minus 3 is equal to y squared. What undoes a square? Square root. Make sure to keep in mind the plus and minus. So I have plus or minus square root of x minus 3 is equal to y. Step 3, use correct notation. So we want to use the inverse of x. So I would have the inverse is equal to plus or minus square root of x minus 3. All right, moving on to the next one. So step 1 in finding the inverse, switch the x, switch the y. We have x is equal to log base 3 of y. Step 2, solve for, so I'll write this was step 1. Step 2, solve for y. How do I get y by itself if it's part of a log? If ever you're stuck with a log, always change it to exponent form. So my base would be 3. 3 raised to the x is equal to y. Step number 3, use correct notation. So 3 to the x is equal to your inverse. And last but not least, it says, the graph of the function is shown on the axis below. Sketch the graph of the inverse on the same set of axes. What you have to remember about a function and its inverse is the domain and the range are switched. That's why we always flip the x and the y. So if I see a point, for example, at 5, 3, I know that the inverse point will be at 3, 5. 1, 2, 3. Right, that's 5, 3. Yep. 1, 2, 3, 1, 2, 3, 4, 5. If I see a point at 4, 3, I know the inverse point will be at 3, 4. If I see a point at 2, 3, I know the inverse point will be at 3, 2. If I see a point at 1, 3, I know the inverse point will be at 3, 1. So this is the inverse part of the graph. And let me just show that that moved to 3, 5. And then if I'm looking at this point right now is at 1, 3. So it's going to move to the point 3, 1, 3. So it's going to move to the point 3, 1. This point here is at 0, 2. So it's going to move to the point 2, 0. This point here is at negative 1, 1. So it's going to move to the point 1, negative 1. This point here is at negative 2, 0. So it's at 2, 0. I already have that one. And then this one here is at negative 3, negative 1. So I know it's going to move to negative 1, negative 3. What's this point? 1, negative 1? Negative 1, 1, 1, negative 1. I feel like this point's off. This is at negative 3, negative 1. So it's going to be at, that's what I did wrong. So that's going to be at negative 1, negative 3. And now I can see that it is indeed reflected over the line y equals x. And that's like a good way to check. Is it reflected over that line? That's it.